Hello everyone, welcome to this lecture. In the last two lectures we studied modal parameter estimation using peak picking method, circle fit method and line fit method. So those were single degree of freedom methods. And today we are going to look at a multi degree of freedom method for modal parameter estimation, and that method is rational fraction polynomial method. So the methods we studied in the last two lectures, they were single degree of freedom methods, and they have the shortcoming that the contribution of out of band modes is not completely or correctly accounted for, and this affects the accuracy of the estimated model parameters. For example, the peak picking method and the line fit method, they completely neglected the contribution of modes which are not in the selected frequency band, right. And because these methods are based on single degree of freedom assumption, the band is selected such that it has only one mode in the band. So those methods completely neglected the effect of or the contribution of out of band modes. And the circle fit method also made an assumption that the contribution of out of band modes is a constant term. So therefore these methods are single degree of freedom methods, and because they are based on single degree of freedom assumption, and hence they fit only one mode at a time, and that is why the narrow frequency band that is chosen such that there is only one mode in the band. And because this affects the quality of model parameters, what is required is to take into account the contribution of other modes also in the curve fitting process. And so with this inspiration, the multi degree of freedom methods were proposed. Okay. So RFP we are going to study today, which is rational fraction polynomial method, is a multi degree of freedom curve fitting method, right, and it takes into account the effect of all the modes which are there in the selected frequency band, right, and therefore it is a multi degree of freedom method. So it fits or curve fits all the modes in the selected frequency band, and this method is going to perform curve fit on the frequency response functions, and that is why it is a frequency domain method. Let us now look at what is the pole residue form of the FRF. The RFP method formulates the curve fitting problem using the pole residue form of the FRF. So it assumes a viscous damping model for the curve fitting. It fits a viscous damping model. So let us first of all look at the pole residue form of the FRF for a single degree of freedom system. Now the single degree of freedom transfer function can be obtained as a ratio of the Laplace transform of the output, right, which is x of s divided by the Laplace transform of the input. And it can be shown that for a single degree of freedom system, this transfer function is nothing but 1 upon ms square plus Cs plus k. Okay. And if we divide the numerator and denominator by m, mass of the system, and then we can write this transfer function in this form, that is 1 by m divided by s square plus 2 zeta omega n s plus omega n square. So here s square plus 2 zeta omega n s plus omega n square, which is the denominator of this transfer function, is the characteristic polynomial. So this denominator, which is this, is nothing but the characteristic polynomial. Okay. So it will have two roots, okay, S1, S2, and those roots are called as the poles of the system, right. And if we assume underdamped system, right, then these poles should be complex conjugate, right. So let us say the roots of this characteristic polynomial, assuming underdamped system, the roots would be S1 and S1 star, right, which are complex conjugate roots. So with this, now we can write this transfer function in the partial fraction form. So we can break this right hand side, the transfer function, into partial fraction form. So we have first term which corresponds to the first pole S1, and then we have another term corresponding to the other pole, which is S1 star, right. So there are two poles, and that is why there are two terms in the transfer function in the partial fraction expansion. So this is partial fraction form of the transfer function. Now we can obtain the FRF from the transfer function by substituting s is equal to I omega, right. So if you assume the complex variable s to be a purely imaginary number, then we can substitute s equal to I omega, and then the expression we get is the expression for the FRF of the system, the frequency response function. So for an underdamped system, the values of S1 and S1 star, they are called the poles, and they are given by minus zeta omega n plus minus I omega n under root of 1 minus zeta square. And if you represent omega n into 1 minus zeta square square root by omega d,
then the poles can be written as minus zeta omega n plus minus I omega d, right. So, these are the poles of the system, and in the FRF we see that each term corresponds to a pole, and in the FRF we see that there are two terms, right, because there are two poles, and for each term there is a constant in the numerator which is called residue, right. So, we can see for this term there is a constant in the numerator which is r. So, this is the residue for this term, and then for the second term we have the constant r star, right, which is the residue for the second term. So, these r and r star are the residues. So, these residues for this single degree of freedom case, they are given by r is 1 upon 2 I m omega d, and r star, which is the complex conjugate of the residue r, is minus 1 upon 2 I m omega d, right, which is this one. Okay. So, that is why we see that this FRF is described by the poles and residues. So, if we look at this FRF is described by poles and residues, and that is why this form of the FRF is called the pole residue form of the FRF. Therefore, if for a single degree of freedom system there are two poles, right, and two residues. So, for an n degree of freedom system there will be 2n number of poles and 2n number of residues, and these poles and residues will be in complex conjugate form. So, there will be effectively n number of complex conjugate poles and residues. So, this is something we have studied earlier in our lecture on the multi-degree of freedom system with non-proportional viscous damping. So, for a multi-degree of freedom system the pole residue form is given by this expression, right. So, here Hjk is the FRF Jk, right, with the response at jth degree of freedom and the excitation at the kth degree of freedom, and this is equal to summation from r is equal to 1 to n because there are n number of complex conjugate poles and residues. Okay. So, the summation goes from 1 to n, and then the sum of rjk. So, this rjk is the residue for the rth mode corresponding to the FRF jk, right, divided by I omega minus SR. So, SR now is the eigenvalue of the rth mode or the pole of the rth pole, and then we have r star jk. So, this is the residue for the complex conjugate version of the rth mode, right, corresponding to the FRF jk, and then divided by I omega minus SR star. So, SR star is the complex conjugate of the rth pole, complex conjugate value of the rth pole. So, here the rjk, this is given by phi jr into phi kr, right, and r star jk is given by the product of phi jr complex conjugate into phi kr complex conjugate, right. So, this is the pole residue form for the multi-degree of freedom system. Let us now look at the formulation of the method. So, the rational fraction polynomial method is based on expressing an FRF of the system in the form of a rational fraction, okay, which is ratio of two polynomials, and it assumes a viscous damping model. It assumes a viscous damping model for the system. So, this is the partial fraction form of the FRF, right, this we have just seen earlier. And then what is the FRF in the rational fraction form? Now, we take LCM of the right hand side, right, and then if we simplify we will get a polynomial in the numerator and a polynomial in the denominator, and that is nothing but the rational fraction form of the FRF. So, you can see this is given by a ratio of, you can see we have a polynomial in the numerator, right, and the degree of this polynomial is m, and then we also have a polynomial in the denominator, and the degree of this polynomial is n, and if there are n number of modes, okay, then the value of small n would be 2n, okay, the degree of the denominator polynomial will be 2n, and the degree of the numerator polynomial m will be 2n minus 1. So, in the partial fraction form, the unknowns are the poles and residues. The FRF, if it is measured, then the variables which are on the right hand side, which are the poles and the residues, which are basically related to the modal parameters of the system, they are the fundamental unknowns. But in case of the rational fraction form, on the right hand side, the unknown quantities are the coefficients in the denominator and the numerator polynomial. So if the FRF is given, that is the h of omega is given, then we need to fit this expression to the FRF and find the values of the coefficients a and b, which are the coefficients in the numerator and the denominator polynomial. And these numerator and denominator polynomials ultimately are related with the poles and residues. So once these coefficients are known, then it would be possible to find out the poles and residues of the system. So that is the idea behind the rational fraction polynomial method. So let us now further look at the formulation of the method. So let Hm omega represent a measured FRF, and let us define difference in the FRF delta H. Okay. So this is the delta H is the difference in the FRF. Difference of what? Difference of the FRF to be fitted. This is the FRF to be fitted. So FRF expression we want to fit, and Hm omega is the measured FRF. Right, that is the measured FRF. So the difference between the FRF to be fitted and the measured FRF is referred as delta H. And now we would like to define an error function which defines the error in the curve fit. So this delta H, if we substitute the expression of the rational fraction form of the FRF H omega into this expression and simplify, then we get this expression. Okay. Now here we see that if delta H we want to make 0, right, because ideally we would like the difference delta H to be 0. We would like that the FRF we are fitting on the measured FRF should exactly follow the measured FRF. That is what ideally we would like to have, right, and therefore ideally delta H should be 0, and delta H would be 0 if the numerator of the expression delta H is 0, correct. So you can see this is the numerator of the delta H. Okay. So if this becomes 0, then delta H would be 0 and the curve fit would be perfect, and that is why we define the curve fit error as the error E omega, which is nothing but the numerator of delta H expression, correct. So you can see this is nothing but the E omega is nothing but the same as the numerator of the delta H. So this defines the error at a frequency omega between the FRF we want to fit, that is the FRF expression, right, we want to fit, and the measured FRF, right. So now what we do, we select now a discrete frequencies in the selected frequency band about which we would like to enforce or force the error E to become 0, right. So, so let us say we have L number of discrete frequencies that are chosen in the frequency band. Okay. So we have chosen a frequency band, and then there are several discrete frequencies in that band, and now we are selecting, let us say, L number of frequency points in that band, right, and let us say those frequencies are omega j, that is omega 1, omega 2 up to omega L. So these are the frequencies. So what we can do now, we can write an expression for E omega at each of these frequencies, right. So we can write or get the error E omega at each of these frequencies. So we will get L number of such error equations, we will have L number of such equations, right. So then we can combine all those equations into a matrix form. We can write those equations in a compact matrix form, okay, and that matrix form is given by this equation. So this is the matrix equation for errors E omega j, right, with j varying from 1 to up to L. So this is the matrix equation. Now what are the these different vectors and matrices which are appearing in this equation? These matrices and vectors are this, right. So here vector E, okay, this vector E is the vector of errors, okay, at L number of frequencies. So we can see here this is the vector of error at L number of frequencies. Then vector A is the vector of coefficients of the numerator polynomial, okay. So this is the vector A, which is the coefficients of the numerator polynomial, vector of the coefficients of the numerator polynomial. Similarly the vector B is the vector of coefficients of the denominator polynomial, right, this one, okay. And then the P, T and W. So P and T are coefficient matrices, and W is a vector. So, these quantities they depend on the values of the measured FRF at this discrete L number of frequency points and the values of those discrete frequencies themselves. So, we can see from here this P matrix, T matrix and W vector, they depend on the measured FRF values and the discrete frequency values, correct. So, it means the P, T and W they are fixed once the frequency points have been chosen, right, they are fixed, right, and the vectors A and B they are unknowns that we do not know, right, and then we would like to find A and B such that the vector E is minimum, that we would like to minimize, right. So, therefore, in order to minimize E we define now an error function. So, let us define the error function as sum of squares of the errors, right. So, we define an objective function J which is equal to E transpose E. So, E transpose E effectively squares the different errors, right, at different frequencies and then takes a sum of it. So, that is nothing but the objective function J, and now we would like to minimize this. So, therefore, this J is now a function of the vectors A and B, right, the unknown coefficient vectors A and B, and the necessary condition for J to be minimum is that the first derivative of J with respect to each of the polynomial coefficients that must be 0, right, and when we enforce that those conditions, right, then we get now two matrix equations which are as follows. So, you can see we get this is the first matrix equation we get when we enforce the condition that the first derivative of J with respect to each of the numerator polynomial coefficient should be 0, and then we get another matrix equation when we enforce the condition that the first derivative of the J with respect to each of the denominator polynomial coefficient is 0. These two matrix equations can be written in a compact matrix form like this, okay. So, you can see this is the equation we are getting now, and these equations you can see they are linear equations, they are linear equations, okay, in A and B, in A and B, and the reason that they are linear because the objective function here J, it is a quadratic objective function. You can see here it is a quadratic objective function. So, this is an important advantage of the rational fraction polynomial method, okay, that the equations that we need to solve they are linear. So, now these equations now they are solved for A and B, there are as many equations as the number of unknowns. So, we just have to solve this equation. So, that essentially gives us the information about the unknown numerator and denominator polynomial coefficients. So, now the question is how do we obtain the poles and residues, because they are finally related to the modal parameters. Now, we know that poles are nothing but the roots of the denominator polynomial, and since we now have information about the denominator polynomial coefficients, we know the denominator polynomial. So, that denominator polynomial is this. So, we can see it is nothing but BO I omega to the power 0, B1 I omega to the power 2 and going up to Bn I omega to the power n is equal to 0. So, this is nothing but the denominator polynomial. Okay, it is nothing but the denominator polynomial, and here BO, B1, Bn are known. So, now we need to solve this polynomial for its roots. So, we can find the roots of this denominator polynomial and they would be nothing but the poles of the system, and the roots of the denominator polynomial can be found using any standard root finding procedure. So, once poles are known and because the coefficient vector A, that is the numerator polynomial coefficients, they are also known, then we need to now find residue corresponding to each of the poles, and this can be then found using the pole residue theorem. Okay. So, the pole residue theorem is this. So, this theorem now you can see this is nothing but the residue for the FRF HJK for the qth pole, right, and on the right hand side you can see what appears are the different poles which are now known, that is SQ, SU, they are the values of the poles, and AK they are the numerator polynomial coefficients which are also known. So, if therefore, the right hand side can be easily computed which will give us the residue for the qth pole, right. And so once the poles and residues have been obtained, how we find the modal parameters? So now from the knowledge of the poles, we can find the natural frequencies and the modal viscous damping factors, because we know that for an underdamped system with viscous damping, the poles are in the form of minus zeta omega n plus minus I under root of 1 minus zeta square into omega n. So if we know the poles, we can find the values of omega n and zeta from these expressions, right. And those expressions are, so omega r, that is the natural frequency of the rth mode, right. It is equal to the square root of the sum of squares of the real part of the pole and the imaginary part of the pole, right. So this is nothing but we get the rth natural frequency, and then we can find the modal viscous damping factor for the rth mode as zeta r is equal to minus into real part of the pole, that is SR, divided by the natural frequency of the pole, that is omega r, which already has been found out. So this gives us the modal viscous damping factor. Now how we find the elements of the mode shapes, right, because we know that the residue is given by product of the jth and kth element of the rth mode. So we know that the residue RRJK, which is basically the residue in the FRF JK corresponding to the rth mode, that is given by the product of the jth and kth element of the rth mode shape. So in this expression we know the residue, already we have found the residues, right, and now we can determine the elements of the mode shape by following the procedure which we studied in the peak picking method, right. We studied there that once we know the modal constants, then how do you find the elements of the mode shape. So that procedure can also be used here to find the elements of the mode shapes, right, and that way we can get the complete mode shape vector. Let us now look at the advantages of rational fraction polynomial method. As we discussed, the RFP formulation requires the solution of linear equations to find the primary unknowns compared to the solution of non-linear problem for multi-degree of freedom curve fit based on the partial fraction form. So there are some other multi-degree of freedom curve fitting methods which require solution of a non-linear problem to perform the curve fit. Okay, solution of a non-linear problem is not straightforward. In RFP, we have to solve linear equations to find the primary unknowns, that is the numerator and denominator polynomial coefficients. Now to obtain the poles from the denominator polynomial, we have to solve a non-linear equation, but finding the roots of the denominator polynomial is not difficult, right, because finding the roots of the denominator polynomial to obtain the poles is much less demanding, right, and well established root finding methods are available. Okay. So although in the RFP also at one stage we have to solve a non-linear equation to find the roots of the denominator polynomial, but finding those roots is not so difficult, right, it is not that demanding, and there are established procedures available to find those roots. So the formulation we have studied till now is referred as the RFP formulation based on the ordinary polynomials, because the rational fraction form we considered, it consisted of the ratio of the numerator and denominator polynomials which are in the ordinary form, and ordinary means those polynomials consist of the powers of I omega as the basis functions, right. So we had the terms like I omega to the power 0, I omega to the power 1, I omega to the power 2, I omega to the power n and so on, right. So they are the different basis functions, they are the powers of the variable which are appearing in the two polynomials. Now one disadvantage of this is that the magnitude of different terms in the polynomial, the difference would be very high, and that would lead to the system of equations which would be ill conditioned, right. So that is the one disadvantage of the RFP formulation based on the ordinary polynomials which we just saw. Therefore we see that the matrix equations we get to solve the coefficients A and B, the coefficient matrix is ill conditioned, which means that if a small error or small deviation occurs in the coefficient matrix or in the constant vector, then it leads to a large deviation in the solution, and because of that the curve fitting will not be accurate and the solution we get will not be reliable. So therefore to address this difficulty, the formulation of the RFP was done using orthogonal polynomials. Okay. So it was proposed to formulate the RFP using orthogonal polynomials. So, what are orthogonal polynomials? So, two polynomials are orthogonal if the integration of their product over the domain is 0, right, and formulation using these polynomials improves the condition of the coefficient matrix. Okay. So, therefore, the basis functions which are used to define the polynomials, the numerator and denominator polynomials, those basis functions are orthogonal. They are no longer in the form of the powers of the term I omega, and because of that the coefficient matrix we get in the final system of linear equations, that is no longer ill conditioned, and therefore the solution for A and B can be carried out accurately, and therefore the curve fitting can be done, will also be accurate. So, this is form of the FRF based on the orthogonal polynomials. So, this is the numerator polynomial based on orthogonal polynomials, and this is the denominator polynomial based on the orthogonal polynomials, right. So, here phi k are the basis functions which are orthogonal in nature, right. So, all the phi k's, they are orthogonal among themselves, and similarly theta k are again the orthogonal functions which are orthogonal with respect to each other. So, in the previous lecture we have studied what are residuals, right. So, we talked about low frequency residual and high frequency residual. Low frequency residual is the contribution of the modes which are on the lower frequency side of the selected frequency band, right. So, if there are any modes to the left of the frequency band we have selected, those make up the low frequency residual, and the modes which are to the right of the selected frequency band outside the frequency band, those make up the high frequency residual. So, how to account contribution of low and high frequency residual in RFP? Let us talk about that. So, adding a residual term essentially alters the degree of the numerator and denominator polynomial. So, let us say we add a term, say let us say low frequency residual to the rational fraction form of the FRF. So, what is going to happen? When we take the LCM, that will alter the degree of the numerator and the denominator polynomial. Therefore, by appropriately selecting the degree of the numerator and denominator polynomials which we have to fit, we can take into account the residuals in the curve fitting using RFP. So, let us take an example. For example, we want to account low frequency residual, right, and if we recall the low frequency residual, what was it? It was in the form of 1 upon minus 1 upon m j k omega square, right. This was the low frequency residual, right. So, we see that if this residual we want to add to the rational fraction form, then the denominator polynomial and the numerator polynomial, their degrees will get altered, it will go up by 2, correct. So, therefore, we can increase the value of m and n by 2, and then we can account low frequency residual in the curve fitting. So, this is the basic idea behind accounting residuals in RFP. Let us now take an example of modal parameter estimation using RFP, and we are going to take a simulated structure, right. We will simulate the FRFs on this structure and use those FRFs for curve fitting. So, as we have done in earlier simulations, we are taking this cantilever structure and there are 5 number of test points, and we are recording the or simulating the FRFs in the translational directions at these 5 points. And let us say we have a row of the FRF matrix that we have measured. So, let us focus our attention on analyzing the driving point FRF H55, right. Receptance H55 we would like to analyze, and let us perform a multi-degree of curve fit covering the first 3 peaks, right. Let us take the frequency band covering the first 3 modes, and we will perform a multi-degree of curve fit in this band. We will also now choose certain discrete frequency points in this band, right, for performing the curve fitting. So, this is the plot of the receptance FRF H55, right. So, you can see this is the plot of the receptance FRF H55, and the rate curve basically is the plot of the FRF, okay, receptance FRF, and the blue dots the points we have chosen, right, and this frequency band is this, right. This dotted vertical line shows the higher limit of the frequency band. So, in this frequency band we have chosen these frequency points. And now let us also model high frequency residual, okay, because we see that the lower limit of the frequency band we have chosen starts from 0, right. So, there is no mode to the left of this frequency band. So, there is no low frequency residual, right. But on the high frequency side you see there will be some modes beyond the
selected frequency band, and then we would like to incorporate the contribution of those modes in the curve fitting process. And now we are going to therefore incorporate or include the high frequency residual, and we are going to use a pseudo mode in order to model the contribution of the high frequency modes which are outside the band. And as we studied earlier, the contribution of a pseudo mode can be modeled as 1 upon k j k minus omega square m j k. So, we can model the pseudo mode like this. So, here you can see there are now two unknowns k j k and m j k, right. So, when this pseudo mode is added to the rational fraction form, it will increase the degree of the numerator and the denominator polynomials by 2. Let us now look at what should be the degree of the numerator and the denominator polynomial of the rational fraction form of the FRF that we will like to fit onto the measured FRF. So, the degree of denominator polynomial will be equal to 2 into 3 plus 2, because there are 3 modes we want to fit. So, therefore, 2 into 3, right, plus 2. So, plus 2 is because of need to account for the high frequency residual, right, and as we said, the degree of the denominator polynomial will increase by 2, and that is why this 2 we have added. So, the degree of the denominator polynomial is 8. Similarly, the degree of the numerator polynomial will be 2 into 3 minus 1, that is 2n minus 1, where n is the number of modes, which is 3 here. So, 2 into 3 minus 1 plus 2 to take care of the high frequency residual. So, therefore, the m will be 7. So, now we set up the linear equations in terms of a and b that need to be solved, right, using this information, and then we solve those equations, right. Once we get a and b, then we can then solve the denominator polynomial for the poles of the system, right, and then we from the poles we can find the natural frequencies and modal loss factors, and then we also get residues, right, by using the pole residue theorem, and from which we get the mode shape elements. So, this is the result, right. You can see we have got the poles. So, there are now you can see 8 number of poles we have got 1 to 8, right. So, you can see this is the first pole pair, right, and this is the last pole pair. Okay. So, there are and they are in complex conjugate form. So, here the first 3 pole pairs they correspond to the 3 modes we have fitted, right, this one, right, while the last pole pair, this one corresponds to the pseudo mode we have included to account for the high frequency residual, and these are the corresponding residues. Now, from the poles we obtained a natural frequency and a modal viscous damping factors, and they are this. So, omega 1 is equal to 2 pi into 9.81 radians per second, right. So, therefore, there are 3 frequencies at 9.81 hertz, 61.54 hertz and 172.86 hertz. Then we have the modal viscous damping factors, right, 0.0283, 0.00452 and 0.00161, and then from the residues we can obtain the mode shape elements. Let us now look at what is the quality of the curve fit we have been able to do, right. So, for that let us now overlay the FRF regenerated using poles and residues, right, because once you have found the poles and residues for the FRF H55, we can use them to obtain or reconstruct the FRF again, and when we can compare that regenerated FRF with the measured FRF that was curve fitted, right. So, that would give us a good indication that what has been the quality of fit using the RFP. So, this is the overlay of that. So, you can see here the rate curve is the measured FRF. So, this is the measured FRF HM, right, which is the measured FRF, and this blue curve is the regenerated FRF. So, we see that in the selected frequency band, right, or the band in which the curve fitting was done, we are covering the first 3 modes, the fit is excellent, and therefore, the multi-degree of freedom curve fit using RFP is quite accurate, right, and it has been able to fit multiple number of modes, okay, and account for their contribution simultaneously. Okay. Let us briefly now talk about what is global RFP. So, the rational fraction polynomial method we studied and the example we saw is it can be referred as local RFP, right, because in this the one FRF was curve fitted at a time, and then all the subsequent FRFs or all the FRFs will have to be then curve fitted one by one. So, such an analysis of the FRFs is referred as a local approach to curve fitting, right, and therefore, the RFP method we studied can be referred as a local RFP. However, we should note that the natural frequencies and modal viscous damping factors, they are the global properties of the structure, right, because they do not depend upon at what point the structure is excited and at what point the response is collected. Okay. And therefore, ideally their estimate should not vary from FRF to FRF. But because of some noise in the FRF and because of small measurement variabilities, there would be some difference that would occur in the estimates of these values, estimate of these quantities from different FRFs. So, what we therefore ideally would like that we should be able to get a single consistent estimate of the global properties, that is the natural frequencies and viscous damping factors or the damping factors, right. And for that, what has been proposed is to analyze all the FRFs simultaneously in order to obtain these properties. So, such an approach to curve fitting is called global approach, and the version of the RFP which analyzes all the FRFs simultaneously is referred as global RFP, right. So, RFP we studied is a local method as it is used to analyze one FRF at a time. And then of course, we have talked about the variation of natural frequencies and damping factors which we get from different FRFs, okay, and then the natural frequencies and damping factors are global properties, and therefore, what global RFP does, it utilizes all the FRFs to estimate the global properties. And how that is done? How that is done? So, we saw that in the local RFP, right, or the RFP formulation we just discussed, we studied, it finds the numerator as well as denominator polynomial coefficients simultaneously, and that is done for each FRF separately, right. So, in the global RFP, the estimation of denominator and numerator polynomial coefficients is decoupled, right. You can see the estimation is decoupled. So, what is done? First of all, we use all the FRFs in order to formulate the problem to find the denominator polynomial coefficients. So, we use all the FRFs to set the equations which give us the denominator polynomials coefficients. Once that has been done, then we solve for the poles of the system, and from the poles we find the natural frequencies and viscous damping factors, right. So, that then would be a single consistent estimate of the natural frequencies and damping factors for the whole system, right. After that, then we formulate the problem okay, to determine the numerator polynomial coefficients, okay, and then that is done for each FRF separately. So, then we find the numerator polynomial coefficients for each FRF, and then we analyze those coefficients to find the residues, right, using Pole-residue theorem, and then we obtain the mode shape elements for that FRF, and then we repeat this procedure for each FRF. So, that way then we can get the residues for all the FRFs, and then we can find the mode shape elements and the mode shape for the whole system. So, in this way in the global RFP ensures that the estimates of the global properties are consistent, and we obtain a single consistent estimate for the whole system. So, this approach is likely to give a more consistent modal model. So, in this way we come to the end of this lecture. So, in today's lecture we looked at the modal parameter estimation using rational fraction polynomial method, which is a multi-degree of freedom curve fitting method. We also talked about how to account for residuals and what is the global RFP, right. So, now we stop here. Thank you.